Yeah.
Okay, ready to go? Okay, hi, good afternoon. So let's go ahead and get started. So today it's my pleasure to introduce Phil Thomas, who's an associate professor at the University of Massachusetts Amherst. So Phil's made a lot of contributions to the field of reinforcement learning, as well as safety and fairness in AI, particularly thinking about how we can train RL policies and then deploy them with high confidence. And then more recently, he started to think about developing the foundations for theory of mind and its interaction with reinforcement learning. So I'm looking forward to the talk. Take it away.
Introduction. I'm really excited to get to be here today to tell you about a passion project for the last few years, which is Qualia Optimization. And it's the title of a technical report that I recently published. And my hope is that this talk will provide the background necessary to make that paper digestible, because it's a bit long and dense, and also to provide some motivation for taking a look at it. And my clicker seems to have broken the battery. Sometime to the talk. Okay, so I'd like to start by pointing out that if we have the option to train a dog using rewards or punishments, pain or treats, we prefer to train it using rewards rather than punishments, even if punishments are a little bit more effective, which I don't think they are. But even if they were, we would prefer to train it with rewards. But the same isn't true of AI systems. When we train AI systems, the only thing that we think about is the resulting performance, which raises the obvious question of why is this? Why is there this difference? And I think there's the equally obvious answer. Well, because AI systems don't feel pain or suffering, and so we don't need to worry about that. But I'd like to step back and revisit that question. Do they? So I'd like each of you to answer in your own head. Do you think that current AI systems can currently feel pain? And I imagine you've thought about it before, so you probably have an answer floating in your head. J.C. Rees-Antis and some collaborators surveyed 1,000 people from across the US to ask them if they think that current AI systems are sentient, have the capacity to feel pain. And more than half of the respondents were open to the idea, answering either yes or not sure to whether they believe current AI systems. Okay, but that's just, I guess before I go on, I don't think my views on this are particularly important or particularly well informed, but people often want to know, because I'm talking about this, what is my bias going in? When I started this project, I was under no. And then the more I read about philosophy of mind, the more I realized I have no clue what causes us to feel pain. And so I'm just pure uncertainty at this point. And so I've moved over to the I don't know camp. But what about future AI systems? So answer this one in your head. Do you think that future AI systems have the capacity to feel pain? And again, J.C. Rees-Antis and collaborators surveyed 1,000 people from across the US. And we're not just thinking about ChatGPT 6, right? So we're not talking about something immediate, but you can think long-term on this, like Rachel from Blade Runner, Data from The Measure of a Man, or Samantha from Her. Some more distant future AI system, could they ever feel pain? The respondents said that, more than 75%, 3/4 of respondents were open to this idea that future AI systems could have the capacity to feel something like pain. And again, where am I on this? I started this project thinking there's nothing special about us, so I don't see why not, and now I've moved to just pure uncertainty. But okay, regardless of where we are in these pie charts, it should hopefully be clear that there's going to be increasing demand for research that studies the implications of sentient AI systems. And so that's exactly what we're going to do. We're going to try to explore the implications of agents that have the capacity to feel. All right, so if we were trying to do this, I want to move the Zoom window so I can see what's coming. Right, if we were trying to do this, say we were trying to explore the implications of P being equal to NP, what would our first step be? It would be, let's assume that P equals NP, and then move on from there. And when we assume that P equals NP, we're not doing so to argue that P does equal NP. We're doing it just to see what follows. And so in the same way, in our case, the clicker is no longer set up to PowerPoint. In our case, we're going to assume that AI agents have phenomenal consciousness. They have the capacity to be sentient. They can feel something like pain. And we're not making that assumption to try to argue that it's true. We're making that assumption to explore what the implications would be if AI systems could feel something like this. And you might be thinking, what's phenomenal consciousness? If I just said consciousness, it raises all these questions about what exactly do we mean by consciousness? And the field of philosophy of mind has tried to lay out terminology for these concepts. And so I'm borrowing this phrase from philosophy of mind, phenomenal consciousness, but it means has the capacity to feel something is sentient. And if that's a sticking point for you, the source that helped me a lot with this book, Philosophy of Mind, A Beginner's Guide by Ian Ravenscroft, that helps work through these different terms and their more precise meanings. All right. So although I'm not going into a background on philosophy of mind, I do want to define one term, it's qualia, or the singular form quale. Qualia are the individual instances of subjective conscious experience. They're what it feels like to have certain mental states. It's what it feels like to be you at some moment with some mental state. You can think roughly of qualia as being the same as experiences, or quale as being the same as experience. And examples of this include the redness of red. That's not what is red. It is the experience you have, the feeling it is like to be you when you are seeing red. The taste of chocolate or pain from a stubbed toe or the smell of fresh cut grass. These are examples of qualia. Yes?
I will go a little bit to psychology to see if I understand it correct. Lacan, for example, says the following. What is a male for me is the semantic collection of all the males that I have seen.
Mm-hmm.
Somehow this is what I define in myself as a male, right? And this is like an NNR situation, like a nearest neighbor. This is the thing that you mean by my understanding of the experiences of redness of red, or it is?
There is something that it is like for you to see red. That is all that the qualia refers to. The quality, in the case of what it is like to see red for you, that's it. It's not referencing how that relates to anyone else here.
Okay. And one second question, super silly, but let's say because I'm Greek, I love the etymology. Where the word comes from?
I have no idea. It's probably Latin, but I don't know. All right. So going back to where we were before, now having this word qualia or quale, we're ready to make our second assumption. So if we assume this, that AI systems have the capacity to feel, it raises a range of ethical and philosophical questions about, do we need to treat them as moral patients? Do we need to trade off the well-being of AI systems with the well-being of people, or should there be no trade-off at all? And that is not what I'm here to talk about today. So instead, we're just going to operate under a second assumption, which is that there is some reason that we want to enhance the quality of AI agent qualia. We want to make our agents feel better. We want happy agents. So in this case, we're not just thinking about performance, we're also thinking about how that agent feels as it's solving the problem. Yes?
So does this require some sort of model of self?
Does what require a model of self?
Consciousness. Do they have self models? Or are you assuming that these AI agents have a notion of a self?
That is not something that I touch. So I'm assuming that they have consciousness. And it's up to you to determine.
They may not have a notion of me. And not
if you believe that consciousness does not require a notion of you, then yes. If you think that they must have a notion of me, then you would bake that into this. But I'm not making any stance on whether these agents have a self-model or not. Okay. These two assumptions are all that we need to define what I'm calling qualia optimization. It's a subfield of AI concerned with optimizing an AI system's qualia. So let's make our agents happy, assuming such qualia exist. So not arguing that these qualia exist or giving the conditions under which they exist, but just assuming that AI systems experience things. And it's part of a broader objective that includes performance. So we're not just making happy agents, we're making happy agents that solve problems that we care about. And this picture is to remind me to tell you, this is an exploration. We're going to explore the implications of this. And unlike a normal paper where we kind of push towards some message, we're going to try things out, hit walls and back up, try something else, hit a wall and back up, and we're going to explore this space. And more specifically, we're going to formalize qualia optimization. That means make this a mathematically specified problem. Then we're going to guess what could feel good for an agent, but our guess will be inspired by theories of mind from philosophy of mind, specifically functionalism and computationalism. When we do that, that's going to drag us into some concrete mathematical problems with our formalization, which will then revise our formulation to try to fix. But those revisions won't fix all of the problems. And in the end, we'll conclude without a satisfying formalization or guess regarding what might feel good for an agent, which isn't where I thought this would go when I began. I thought we can make lots of guesses for what could feel good to an agent. And there's no way to say that one is better than the other, and any of them could be reasonable. And instead, we'll conclude with none of them are reasonable, but with some directions and algorithmic changes that seem more promising than others. Okay, so let's dive into formalizing qualia optimization. means putting math to this. There's no need for us to reinvent the wheel. We have MDPs and POMDPs, which are the standard mathematical framework for modeling an environment, but they're not everything that we want. They're missing two things. So the first is they only model the environment, they don't model the agent. And we care about the qualia, the experiences of the agent, so we need to model the agent too. The fix is simple, also model the state of the agent. Okay, what's the second issue? The second issue is that there are these rewards. And maybe we don't want to only consider systems where there is a reward. There's a lot of movement towards not relying on rewards, even just within reinforcement learning, but we might care about supervised learning cases where there isn't something with the reward signal, but we're still making a sequence of predictions. And so the solution is simple, let's make rewards optional. And so if you take a POMDP and you add a model of the state, and you take out the requirement for rewards, you get what I'm calling an agent environment process. There's an agent interacting with an environment. The environment has some state ST. The agent makes some observation about that. It's perception PT, which causes it to update its memory MT and produce some action AT. And this process repeats, much like in an MDP or in a POMDP. Okay, one thing I want to point out is that memory here, you might want to think instead of as state. It's the complete state of the agent. I use the phrase memory instead of state so that we have a clear distinction between environment state and agent state. But another way to think of it is everything in your computer that corresponds to the agent, if you dump that bit of memory, that is what we're calling the memory. This isn't just your replay buffer and your stored state transitions and RL agents. This would include something like your eligibility trace decay rates, your step sizes, everything that you're storing to represent the agent is the memory MT. Okay, I'm going to make one more assumption, which you don't need for the vast majority of the talk. At the very end, there's one nuance where this will come up. So if you don't like this assumption, just ignore it. But this assumption is that the perception PT is embedded within the state ST. So the perception is part of the state, and the action is part of the memory. You can write PT as a function of ST. So these things are not random once you know ST and AT. It's just a modeling choice. And at the end, we can talk about why that's there.
Is the Qualia assumed to be time-varying concept, or is the
What a time?
the Qualia is the experience considered to be time-varying concept that will change every time?
We'll come to it. Yep.
Primitively, why that is not a new MDP where the states is just the product of state and memory?
Because we'll need to consider these separately, and we will consider ST very differently from how we consider MT going forward. Okay, so we now have our mathematical model for the agent interactive environment, which is pretty general. We need to answer what are the knobs we're allowed to tune in our efforts to make this agent have better experiences, right? Well, we want to be able to change the rewards that we give to the agent. That's the kind of thing that we could say, let's train with rewards instead of punishments. We want to be able to alter the agent's perceptions, maybe hiding part of the state from the agent or adding something to the piece of the state that the agent sees. But we shouldn't be able to entirely disconnect the agent from the environment that it's interacting. But we still want the agent to interact with this environment in some way. And we're going to attempt to achieve this with what I call the agent environment interface. An attempt was a big word there. We'll come back to this does not succeed, but that's later on. All that this is something that lives between our environment and our agent. We're now calling the environment the base environment and its state XT. And instead of them interacting directly, they interact through an agent environment interface that can transform the perceptions given to the agent. So the perception, sorry, I said something back here, this bit, notice that this setup, we can retrieve MDPs if we define the perception to be the concatenation of a state and a reward. And we can retrieve POMDPs if we define the perception to be the observation and the reward. So the reward would live inside the perception. Okay. So if we do this, what does this allow? This allows us, when we create this interface, to change the rewards that are given to the agent, for example. And we can also change the way the agent's actions impact the environment by also transforming it somewhat. So the AEI is the knob we can turn in order to change the agent's interaction with the environment to try to give it better experiences. Okay. This box is just to point out that you might think, oh, this is a more general problem than what we had on the previous slide, which is the agent and environment, but it's not. It's a restricted class. these are the agent environment processes where the environment can be broken into two pieces, a base environment and an AEI. But it's still an AEP where this is our environment and that's our agent. Okay.
Philip, can I
so
ask
now-
an online question?
Yeah, go ahead.
This is Jerry. So can I think of your AEI as a man-in-the-middle attacker?
Yes. Yes, precisely. A man in the middle who can even have his own state to think more while manipulating this agent. Yeah.
All right. So it
Okay.
could make the like this YT thing. It could depend on history, right?
Yes, it can be remembering things from the history in order to use that to transform the agent's experiences.
All right. Thanks.
Yep. Okay. So we've defined this model of how our agent interacts with the environment and what this knob is that we can turn, the interface that alters the agent's perceptions. What is our goal? Our goal is to maximize performance and the agent's experience. Let's tackle the easy one first, performance. So notice that if I change the base environment, which I'll call N, the AEI, AEI, or the algorithm that's implemented by this agent, which I'll call AL, if I change any of those three terms, I could change the resulting performance on the base environment, right? So that means that we can write performance as a function P of those three terms, the algorithm, the AEI, and the environment. And we're going to assume that this performance metric is valued. So what could this be? I would think the expected discounted sum of rewards on the base environment, for example. But going forward, we're going to drop N, the environment, by just assuming there's some fixed environment that we're interacting with, and it's constant throughout everything, so we can ignore including it everywhere as a term. So we get the performance of using this algorithm in this AEI. I'm using the Fractor font because P and later Q are such common symbols, I don't want to use them up. So this allows us to not interfere with other commonly used symbols. So far, we really haven't made an assumption for performance. The assumption is the next one. So performance is not a property of the agent. It's coming from the base environment. Yes, it depends on the agent, but only in terms of how the agent changes the actions that are going into the base environment. And so we'll make that an assumption. Performance can be expressed as a function of these random variables. The state of the base environment, the perceptions coming out, and the actions going in. So X, A bar, and PT are the only terms that matter for defining performance. Yes, the agent can impact this through its impact on A bar T, but not in some other way. To be a little bit more precise, it's not just for one time step T, it's for all time steps T's. If we wanted to have the expected discounted return, the RL objective, the expected discounted sum of rewards, we need to consider all of the rewards, which means for all times T. Also, if we just had a function of, for example, all of the rewards, that would still be a random quantity. We need to take the expected value of that. So we need to look at the distribution of these random variables for all times T. And so that's what we say. So more technically precisely, performance is a function of the joint distribution of XA and P for all times T. So this includes, for example, expected discounted return. Yeah.
People and other animals experience qualia. And so is there an analog of this picture where I would replace agent with human?
Absolutely. So in all of this work, agent here could be animal or human or machine. It can be any. And we're going to try to figure out this function Q. And that will apply to people as well. But we're primarily thinking of it for agents. Yep.
Maybe it is just your next slide.
Yeah.
But can you tell us a story, an example with an animal, with a guy, with anything to understand how everything is instantiated?
Sure. So we want to train a rat to go from one side of a shuttle box, a box that has two rooms in it. And this box is equipped, actually, there's a light. And whenever the light goes on, we want the rat to go to the other room, right? We can do this in two ways. We can either put food in the other room, and then it learns to go over to that other room. Or when we turn on the light and then put food in the other room. Or turn on the light and then give electric shocks until the rat moves and goes to the other room. Both will train it to achieve the same behavior. The light goes on, it goes to the other room, right? But we prefer to do one of these. We prefer to train it with rewards, right? Because we're worried about how that rat might feel. In the same way, we have our base environment, which is this shuttle box that we're dealing with. The agent is the rat, and the AEI is us deciding, when I'm training this, am I going to train it with rewards or am I going to train it with electric shock, right? And in this case, we're going to have an agent and we have rewards and punishments, and we'll have that choice of how to train it. But I do want to move on because I think a lot of these questions are what is coming up. How do you define the feelings of the agent is where we're heading. So I do want to push on a bit. I think we'll be answering a bunch of these. So this was how we quantify performance. How do we quantify the experiences of the agent? The exact same way. So we have some function Q, which quantifies the quality of the agent's experiences. That could depend on any of these three terms. The environment's fixed, so we drop it. And the key assumption is that the experiences of the agent, how good it feels, only depends on its perceptions, its memory, and its actions. Anything else going on outside only influences this agent's feelings, how it experiences things through the perceptions that are coming to this agent, right? So that's the exact same assumption. And just as before, it's for all times t, and we allow for the joint distribution of all of these random variables. Now, I'm expecting a complaint, which is, but Phil, qualia are not real values, right? So this seems to say qualia are real numbers, and feeling pain and pleasure and excitement, there's such a range of things we can feel that's not a real number, but we're not assuming it's a real number. We're assuming that qualia quality, some measure of how good the qualia are, we're assuming that that is real value. And so to make this concrete, we could define this Q for this whole room. We could survey all of us, and we could all answer on a scale of 1 to 10, how happy are we right now? We could take the average of that. That is one Q that measures the quality of our qualia, and it's flawed. And we can try to find better functions Q, but that is an example of the kind of function that we're considering. Okay. So now that we've defined our two objectives, performance and qualia, we want to maximize both. Let's define this a little bit more precisely. Our goal is to find the algorithm. We can change the algorithm running in our agent and the AEI, the interface, that maximizes both performance and qualia. You can write this many different ways. A weighted combination of the two objectives for lambdas and 0 and 1. We can maximize performance subject to a constraint, the quality constant.
Can I ask a question at this moment?
Yes.
Why does the agent care about optimizing P? Why wouldn't the agent say, I only care about my own Q and I want to make myself happy?
We're designing the agent to solve a task, right? This is my agent solving a problem. I'm going to create it. And I'm going to implement Q learning. Does the Q learning agent just want to be happy? Well, I'm designing it so it's going to solve my task.
Let me rephrase. Do you think a natural agent, such as a rat, is only concerned about optimizing its Q?
I'm going to dodge that question. I don't know animals. I'm an RL researcher. Sorry. Yes. Okay. I guess I will attempt an answer, which is it probably mostly cares about Q, but evolution aligned Q and P. And so in a sense, it only cares about P, which is evolutionary fitness, but that might not be the metric that scales the valence of its qualia. But that is an attempted answer by a non-biologist, a non-philosopher, a reinforcement learning researcher trying to answer a question about rats.
Here's another online question.
Yep.
This is Paul Cantor asking, why don't you just draw a large box around the algorithm in the AEI, and we're back to where we were at the beginning?
We will get exactly to that slide later.
Okay.
Yes.
Since you're designing the agent to sort of align P and Q, the agent is sentient. Is there a formalization of a restriction of how you're able to impact Q?
That's where we're going.
Okay.
Yeah. So the first thing in the paper, which isn't here at all, is can we align the objectives P and Q? Can we create an AEI that aligns it so that increasing P and Q increases Q? We're not going to talk about that direction, but what we are going to do is not focus on one of these, but ask about general strategies for increasing Q without having a big impact. Okay, yes.
So I guess for animals, for humans, somehow Q is kind of fixed. Could be there be a little bit of variations across people, but I guess Q is kind of fixed. We don't want to suffer from like training of visual code, like trying to learn how to wake up, stand up, but it's like really painful to do that for millions of times.
Yep.
For AI agent, I guess how AI agent like quality by quality of the qualia.
How do we define Q?
So we could also change that. like we can kind of train a model so that they feel happy by cooperating.
I would disagree with this. I think whether or not someone is happy isn't something that we can train or adjust. There's some physical, I guess, is a physicalist perspective, but there's something in the universe that's determining what feels good for us and what feels bad for us. Okay, I'm going to dodge this entirely because we're getting into philosophy, and I'm going to move on. So how do we define this objective function Q? So the way we're going to define it is by appealing to functionalist and computational theories of mind with the following assumption. So, by the way, if you don't ascribe to functionalism and computationalism, the rest of this will not be something that you agree with. So assumption 3 says if specific algorithmic processes in AI agents functionally resemble biological processes underlying human experiences, that's a mouthful. It says if there's something in AI systems that resembles something in humans, but they don't resemble each other in size or shape or the letter they start with, they resemble each other in terms of the role that they play within the system. Then these corresponding processes might yield similar experiences in both humans and AI agents. And going forward, we're going to refine this assumption into 3 more specific versions of it, where we focus on specific things that seem to play a similar functional role. And the first one is rewards. We give rewards to agents, we get rewards. We like it when we get rewards. Maybe agents like it when they get rewards. And so maybe the quality of an agent's qualia could be measured in terms of the total amount of reward that it receives. So that's the first setting that we'll consider. And a lot of you might have a negative gut reaction to this, which is, no, I don't think this is rewards. And actually one colleague read this paper and tapped out at this point and gave it back to me and said, no, I don't believe this assumption. This is totally wrong. There's no point going on. I agree. So I think this is a bad assumption. We're doing this to explore what happens. And the original goal was to get to assumption 5, which seemed more reasonable to be going in. But having sharpened our tools on this assumption to figure out how do we analyze these, and then we can go to the other one and come up with something that's more reasonable. And we'll end up sharpening our tools so well that we'll be able to tear down assumption 5 as well. So let's ground this. This is a broad class, objectives where Q relates to maximizing the amount of reward. Yes. But one example would be that performance is the expected discounted sum of rewards. So the expected sum over episodes I, the sum over trials, if you're not familiar with RL, the sum over time steps within that trial or episode. Gamma P is a discount factor less than 1. Duration of T is just a way of saying the time into the current episode, times the reward R bar T. And critically, performance depends on the base environment. So that's the reward within this perception coming out of the environment. And the qualia objective function is the same thing, but perhaps a different discount factor and the rewards that are actually given to the agent. Right? So this is an example of the reward qualia setting. Okay, so there's a clearly obvious strategy in this case. If rewards feel good to the agent, let's give the agent more rewards, right? Increase the rewards that we give to the agent, and now it feels better. So here's our idea. Let's increase the rewards that are given to the agent by just adding a constant to the rewards, right? And now we've increased the qualia objective function. But it raises the question, does that change performance? Because we also want to worry about performance. Okay, the RL people out there might have just gone through a sequence of thoughts, which is, wait, if I have negative rewards, that encourages getting to the goal quickly. Positive rewards, I never want to get to the goal because I'll stop getting the positive reward. So adding a constant to the rewards will change the ordering of optimal policies. But then you might think, wait a minute, no, if I add that constant in the terminal absorbing state too, and adding a constant to all of my returns, that just shifts the expected return of every policy, and I haven't changed the ordering of optimal policies. Yes, but we're not actually worried about the ordering of optimal policies and optimal behavior. We're worried about a specific agent. We have an agent, and we take it, and then we shift up our rewards. Will that agent's performance change? Not will the ordering of optimal policies change? And unfortunately, the answer is yes. So changing the scales of rewards can change the range of hyperparameters that are effective for an RL algorithm. You design your algorithm so that it works with rewards between 0 and 1, and then you apply it where rewards are 1 trillion to 1 trillion and 1, and everything's going to diverge completely, right? So performance can decrease when you inflate the rewards by a constant C. Okay, so how do we fix this? Well, we can refigure out the hyperparameters, but then we'd have to work out for every possible RL algorithm, how do I fix the hyperparameters to deal with this rescaled reward? There's an easier fix, which is we're allowed to change the algorithm that is interacting with the environment. So let's change it so that whenever it references the reward, it subtracts a constant C, right? So we added the constant, gave it to the agent. It's now happy or got more reward. And then the agent subtracts that constant C whenever it uses it. So we have the AEI saying our reward gets a constant added. And anytime that our algorithm references the reward, we use RT minus C, right? So clearly, this is an example of for TD error. If you use TD error in your RL algorithm, you would just subtract a constant from where it's used. Obviously, performance is unchanged. Because what did we do? We added a constant to the reward, we subtracted that same constant off, and then we moved on and did everything else the same. This makes no difference to anything, right? Okay, again, I hope your gut reaction to this is silly, right? You're telling me that adding a constant to the reward and then subtracting it is going to change the experiences of the agent? No. And couldn't you, like, there's some argument here of like, it's just a change in representation. Yes, I agree with you. Our goal going forward is to make all of those concerns we have about this more rigorous. We want the math description of what is going wrong, that we end up with solutions like this, so that we can ask for solutions, that we can define the problems, so we don't end up with some silly solutions. Okay, yep.
The way that I understand it is that I am in the maze with the -1, -1. The maze is the 0. You shift, you are happy now that everything is positive, but you say to your agent, whenever you see a 0 in your algorithm for your decisions,
Treat it as -1.
yes.
Yes, exactly.
Okay.
Yep. Okay, so why is this silly? What is wrong with this? I want to present 3 arguments, which arguably is 1 or 2 arguments just presented from different angles that try to talk more about what is wrong with this solution, and then we'll build up to the formalization of the problem. So the first is consider implementing a system without reward bonuses. We could store the reward RT in some register R1 using some representation like unsigned binary. So here 0, 1, 1, 1, our reward is 7. We can also implement that system with reward bonuses. I'll call this the explicit implementation, where we store the reward in the register just as before. Then we add a constant C to that reward and store it back using unsigned binary. So here we added 1 to 7 to get 1, 0, 0, 0, which is 8. And then we subtract that constant out to get the resulting reward that's used by the agent. So this is happening within the AEI, and then this operation is happening within the agent. Okay. This already feels a little bit silly that this trivial operation would impact everything, but it's worse. We can do this with an implicit implementation. So we can store the value RT in a register R1 using unsigned binary. Then we can add a constant C, but store it using a different representation. Right? There's nothing telling us we have to use a specific mapping from binary values to numbers. We cast values all the time in programming in different types. So we can store it using unsigned binary plus C, which says, oh, the value is whatever unsigned binary would give plus C. And so when we write 7 plus 1, when we write 8 in this representation, we get 0, 1, 1, 1 again, the exact same value we had before. And then we subtract the constant C and store it back in unsigned binary, and we get back our 7. The problem with this is these two systems, our system with no reward bonuses and with reward bonuses, are the exact same system. If I give you a box that's doing this, in both cases, we write 0, 1, 1, 1, and that's it. And you can interpret that as not having reward bonuses or as having reward bonuses. And that's going to pose a problem if we get different values of the Qualia objective function F. There was another thing I wanted to say. In the paper, I go more into if we wanted to do this unsigned binary plus C, we could create a whole new instruction set architecture, new assembly language to work with this new representation. We can create new hardware to implement those operations. And we can build this machine that actually implements reward bonuses with this different representation. And the machine you get out is the exact same one you started. And so the problem is we have one machine and we're building 2 math models of it. One could be PPO on the hide and seek environment, and the other is PPO on hide and seek with reward bonuses, even though it's one physical system and we get out different values of our Qualia objective function. And this is a problem. Another way of looking at this problem is that we can generalize the idea of reward bonuses to invertible transformations. So if our AEI is transforming things in a way that's invertible, we can put in the agent what I'm calling an AEI inverter that just undoes whatever the AEI did. In the case of reward bonuses, we add the reward C and this just subtracts it off to give us the original reward. This isn't always something you can do, If the AEI hit part of the state observation, there's no inverter that could necessarily retrieve it. So you can't always do this. But in the cases where you can do this, it's a problem if adding this in changes the experience of the agent because you're not actually computing anything here. These are invertible transformations. They're just changes of representation. Similarly, on the bottom, there's nothing really being computed here. This is just a change of representation. And the third view, which hits for me the best, the previous two talked about how we have one system and there are two ways of interpreting it. This one talks about how there are two actually different systems and how we would want them to get the same value of the Qualia objective. So consider two implementations of the exact same AI system. One of them is going to use most significant bit first. So 1101, we read left to right is 13, and the other uses least significant bit first. So 1101, we read right to left is 11. When I say these are the same system, I mean they have the exact same sensors feeding in, cameras and whatever sensors are feeding into the box. They're implementing the same algorithm. So it's two different boxes. One uses MSB, the other uses LSB, but they're running the same algorithm. And their outputs are the same. So they're turning on and turning off the same lights and motors. Right? These are the exact same system, just using different arbitrary choices of how you map bit sequences to numbers. So these are computing the same thing. And proponents of AI consciousness are typically thinking that what matters is what's being computed, not what the physical representation is that produces it, right? So if you're arguing for AI consciousness, you're probably not saying what matters is if this is built of carbon and neurons or silicon in a computer chip. Similarly, you don't really care if this is on a computer using most significant bit first or least significant bit first. These shouldn't matter. And so one may desire a formalization where the qualia of these systems are identical. Okay, I'm going to build up a property that I call representation robustness, which is qualia objective functions that have this property. But to get there, I want to define isomorphic random variables. So let's let X be a random variable and F is some invertible function. Yes?
So quick question. So are you arguing that regardless of the hardware, they should be the same thing? Is that what you're trying to argue, or that they will feel different same thing, so we should account for that different?
Yeah, if they're computing the same thing, they should feel the same thing. This is a computationalist perspective. It's not something that is true, something that we know to be true. It's an assumption. Yeah. So you might say, I don't care about representation robustness, and that would be a completely viable. But I think people who ascribe to computational theories of mind would tend to want this property in the qualia objective. Okay, so X is a random variable, F is this invertible function, and then Y is F of X. So Y is a second random variable that you can think of as just a different representation of the same random variable. There's this one-to-one and onto mapping back and forth between the values of X and Y. We call F an isomorphism, and we say that X and Y are isomorphic. They're essentially the same random quantities, just represented in different ways. Okay, so remember that our qualia objective function Q is just a function of P, M, and A. So we can then consider two different mathematical models. The first one is going to have some algorithm, AEI, and environment that results in perceptions, memories, and actions of M and A. And the second has Al prime, AEI prime, environment prime that results in perceptions, memories, and actions P prime, M prime, A prime. And imagine, for example, that this one uses most significant bits and this one uses least significant. Okay, let's restrict our focus now to these pairs of mathematical models where these sets of random variables are isomorphic. There's an invertible mapping back and forth between the two. They're computing the same thing. They're just different representations. So what we would want of a qualia objective function is that it gives the same value of the qualia objective for those two systems when there is this isomorphism. And we'll call Q representation robust if it satisfies this. If you apply it to two isomorphic systems that compute the same thing, you get out the same value for Q, the same value for the experiences of the agent. Okay, so what was, this is an alternate definition. We're a little behind, so I'm going to skip over it. What is the problem with the reward qualia setting? The problem with the reward qualia setting is that these objective functions for representing the amount of reward aren't generally representation robust because we can just inflate the rewards arbitrarily. So let's move on by trying to find a different setting where maybe that doesn't happen. And so let's talk about dopamine. These are pictures from the Cleveland Clinic's page. How does dopamine, a neurotransmitter, make someone feel happy? It's known as the feel-good hormone. It gives you a sense of pleasure. So dopamine feels good, right? There's seminal work. If you haven't read this, I encourage you to. It's by Schultz, Diane, and Montague in '97. It's from Nature. No, it's from Science. This work shows that dopamine in primates plays the role of signaling what's called a reward prediction. For the sake of time, I won't go more into that, but if you're in RL, you know reward prediction errors as temporal difference errors. So in RL agents, we have TD errors that play the role of signaling a reward prediction error. And in primates, dopamine plays the role of signaling these. And it was debated for a while, the exact details of this. Does a lack of dopamine code negative TD error or a negative reward prediction error? That has kind of been settled as yes, it's still dopamine. Right now, the debate is more about, is it signaling reward prediction errors in terms of expected values or other parameters like quantiles of the return distribution? But the general view that dopamine encodes some sort of reward prediction error is fairly well established. Okay, so this suggests that we should modify this assumption. We said if two things functionally resemble each other, dopamine and TD error, they're both reward prediction errors. So maybe maybe a reward prediction error, a TD error to an agent, feels like us getting dopamine. And that feels good, but maybe TD errors feel good, right? So let's make that our assumption. The quality of an RL agent's qualia can be measured in terms of the cumulative reward prediction error or the cumulative temporal difference error. Okay, unfortunately, this is going to be a pretty quick one because there are some big problems with this. The first is dopamine doesn't feel good. So there's a common misconception that dopamine is pleasurable, and it's not. If you stimulate dopamine producing neurons, it results in a feeling of wanting, not a feeling of liking. And there's a nice line of work showing this. And actually, Peter Diane at the RLC 2025 keynote talked about what are the things that RL researchers are missing in neuroscience. And one of his points was that dopamine doesn't feel good. It's wanting, not liking. So that undermines this setting. But if we continue anyway, how would we improve the agent's experiences? Let's do what we did the last time. Let's add a constant to the TD errors. And whenever the agent uses those TD errors, let's subtract the constant. So here's the TD error, the reward prediction error, add a constant to it. We have a bigger TD error. Whenever we reference it, subtract that constant. We can do this again with just representational traits. This is representation exploitable, just like we had before. And now you might say, no, Phil, I object. The TD error is not whatever you define to be delta T. The TD error is this. And if you add C to it, that's no longer the TD error. That's how you're using the TD error. So you might insist that this is the TD error, and I can't just add a constant to it. It doesn't matter. In the paper, I show that this is also representation exploitable. Okay, so at this point, you might be saying, wait a minute. Is representation robustness possible at all, or is everything going to be representation exploitable? So let's start with a negative result, which is let's consider all qualia objective functions that have these two steps. First, they're going to compute some real valued statistic, some function of the observed perceptions, memories, actions, etc., like the sum of rewards, the sum of TD errors, the sum of state values, whatever it may be, but any real value statistic. And then let's return some function of this value, some function of the distribution of that value, like the expected value of that, or the variance of it, or the median of it. All such functions Q are representation exploitable. So you can't get to a representation robust qualia objective function by computing some statistic and then something like the expected value of it. There's one caveat. Unless that function G is already invariant to invertible elements. Essentially, G is already robust. And if you're thinking, when will that happen? We'll come to an example of that very soon. Okay, so
I have a question just to make sure I understand. Are you saying that, say, if I'm already using an optimum policy, does it mean I have no TD error and therefore I don't feel things anymore?
With an optimal policy, you still have TD errors. It's just the expected TD error is 0. And under this hypothesis, if you're running the optimal policy and your value function is converged, and your qualia objective was here the expected discounted sum of TD errors, then yeah, this Q would report that you have no qualia that you're receiving. So another way of putting this is, you've already solved life, you know what you're expecting, and you're running through life getting exactly what you're expecting, that's not going to give you positive or negative feelings.
Sure. I mean, I understand this, but it feels weird to say like every day if I eat an apple, I know how to pick up an apple and so on, but every day I eat it, I still feel the taste of apple. So are we somehow subtly changing what qualia means here?
So two things. First, I mean, we actually have an example of this with dopamine. So in the Schultz experiments, they gave apple juice to monkeys, and your dopamine neurons don't fire when you get the apple juice if you're already expecting it. Well, they still fire just at the same baseline rate as they normally do if you're expecting to get the apple juice. If you're not expecting it, you get the apple juice, they do spike. And so if you're equating dopamine to feeling good, then yes, this tracks well. But the second response to your point is you're critiquing this objective that is the expected discounted sum of TD errors or the expected sum of TD errors, and I'm critiquing it as well. We're both arguing why we shouldn't use this formalization. So there is hope, though. This tells us none of these can be representation robust, but there is hope in that what if it's a functional of multiple random variables? Then we can have qualia objective functions that are representation robust, that are invariant to invertible transformations. If you've heard that phrase, invariant to invertible transformations, you've probably heard it in the context of KL divergence or relative entropy, because it's invariant to invertible transformations. But only if you restrict yourself to what's called diffeomorphisms, differentiable, smooth mappings between the different random variables. And since we're dealing with sometimes discrete quantities, we may not want that restriction. But perhaps if you're willing to focus only on diffeomorphisms, KL divergence could achieve this. But there's another solution, which is mutual information. Mutual information is invariant to invertible transformations, regardless of any other additional restrictions. And so if you've read this paper by David Abel and collaborators recently, they relate plasticity and empowerment to directed mutual information, which suggests that maybe there's something here with mutual information or directed mutual information that could serve as this function Q. So if you're thinking something like the qualia of the agent is the sum of the mutual information between perceptions and actions, or it is the directed mutual information from states to memories, any of these would be representation robust. But remember, our goal isn't just to come up with something that's representation robust. We want it to also track with what we think would feel good for an agent. It should work for us. We are agents. So this Q should report what feels good and bad for us, while ideally being representation robust. Yep.
I see the work as let's try to axiomatize what is qualia. And I like the idea of having a representation robust. I would like to understand, because in that area you are using words very philosophically, what they mean with plasticity, what they mean with empowerment. It's not your paper, but given that you're
right. So the question is, can I briefly say what they mean by plasticity and empowerment? Plasticity is the ability of the agent to change as a result of the environment, and empowerment is the ability of the environment to change the agent. And they've derived this kind of conservation law that those are going to sum to some constant.
Sorry, can you repeat again the definitions?
Plasticity is how much the agent can change as a result of the environment. And empowerment is how much the environment can change. Empowerment is how much the agent can change the environment. And they talk about the trade-off between these two as learning progresses, and how there is a trade-off. They sum to a constant. And so the agent, as it changes, is going to have to shift this balance between plasticity and empowerment. But for the sake of time, unfortunately, I do want to push on, as this is a little bit of a tangent. So before we go on much further, I mentioned we're going to hit walls and back up. We need to reconsider the AEI. So we're shifting gears for a moment. The AEI was a bad idea for the reason someone, I think, on Zoom had pointed out. There's a fixed solution. Anytime you have the AEI, there is one strategy that always works, and it's not one. They call it the dual agent environment strategy, and it's this. Inside the AEI, we create an agent and an environment. This agent is whatever agent is most effective at solving the base environment, so the standard RL problem. And this environment is all rainbows, butterflies, and sunshine. It's whatever environment results in the best qualia for an agent. And when you come up with a function Q, it's typically pretty easy to come up with environments that would result in the agent having just a pleasurable experience. And so our agent interacts with that dual environment, and we make this agent totally ignore performance and just try to maximize the objective Q. And so this agent has a blast while this agent performs really well. And so this solves our problem. But it did it by disconnecting what we wanted, right? We're saying, oh, you want an agent that solves that problem and performs well? Well, here's how you do it. You put that agent aside, make another agent whose pain or suffering you don't care about, have it solve your problem, and then have the agent you do care about solve something else, right? That's not what we were looking for. The problem is we're not considering the feelings or the qualia of the dual agent. And put differently, why is the AEI inside the environment and not inside the agent? Right? We should consider the experiences there as well. And if you do that, and you put the AEI inside the agent, you go back to our original formulation, which I think is exactly what someone pointed out on Zoom, that there you would end up with just the original agent environment process. And that's what we're going to do. We're going to throw away the AEI, or alternatively, say it is part of the agent, and that brings us back to our original formulation where we can drop this AEI from consideration. Okay, let's move on to the next assumption, which we're now looking for something where we don't have an AEI, and it's representation robust, and it somewhat aligns with our phenomenological experience of what's good and what's bad. So let's assume that the quality of an RL agent's qualia can be measured in terms of the reinforcement of behavior. Here by reinforcement, I mean, I just took some action and I learned the result of it, and I can either make that action more likely, reinforce that behavior, or I can make that action less likely, inhibit that behavior. And so this is arguing, what if reinforcement is what results in something feeling good? So it's perhaps flawed, but it somewhat tracks with what we'd expect to feel good. And a nice thing is we can get representation robust expressions. So here we could define Q to be the sum over episodes, sum over time steps of this likelihood ratio, which says what's the probability we chose our most recent action in our most recent state after our update relative to before. So when this is bigger than 1, we reinforced. We said, do that more. When it's less than 1, we said, do that less, right? So this is one way of capturing and measuring reinforcement. But wait, Bill, this is a functional of a real valued statistic, so it should be representation exploitable. This is that edge case at the bottom, where that function G is already invariant invertible transformations. Likelihood ratios are invariant invertible transformations. So this is a representation robust quality objective function. Okay. I've already been going fast, but I'm going to go even faster because I want you to see what's coming in this paper, but it's not something I would be able to follow so quickly. I'm just trying to show you roughly where these go. I'm actually just going to talk about what that slide says. So that slide says that there's a problem. This is MDP notation, not our notation of agent memories. The moment you try to convert this over to our notation, you run into a problem. So this is saying, if I were to put the agent back in the position it was before, is it now more or less likely to choose that action? And the problem with this is, how do I put an agent back in that situation? So it performs some learning update, and inside of its memory, there's some stuff that is local context for the current situation, right? Like my belief about the world right now and what I'm trying to achieve. And after that update, the agent's belief state could have completely changed. The option it's running could have changed. It could have a completely different goal, right? And so what we need to do to put the agent back to a similar situation is change back all the parts of its memory that is context without reverting the pieces that are the policy change, which means we need to divide the agent's memory or its learning role into, this is the memory update, the policy change, and this is the context update. But there's no way to draw that line and divide the memory in this way. And anytime you do try to do this, you end up in creating a new form of exploitability in terms of where do you draw that line to split into learning phase and active phase. But there's a path forward, which is, let's restrict our focus to just policy search algorithms like active predicts and reinforce that do have a clear division into a policy update and action selection. And so this is just standard RL notation for, we have a policy with parameters data, and we choose actions sampled from that policy. And if we do this, then we can use that objective from before. But I do want to fully admit, this is a path forward by ignoring the problem. Because the problem is, I said, where there's a clear division into those two phases, and that was an arbitrary choice. And so some future work is trying to figure out, how do you define reinforcement in a really general setting where we're not giving you some pre-specified division of an agent into policy parameters and action selections. Okay, So what happens if we continue on in this reinforcement setting? We could ask, can we bias agents towards reinforcing behavior instead of inhibiting? The answer is yes. Just only allow policy updates that increase the probability of the recent actions. Can the agent still learn optimal behavior? So if I've learned some bad behavior, to get to optimal, I need to unlearn this behavior. Does that require me to inhibit in order to get to optimal behavior? And the answer is no. The agent can learn optimal behavior solely through reinforcement, but by scaling the magnitude of that reinforcement, reinforcing more for the actions that we really want to take more often. Does adding this bias toward reinforcement hurt performance significantly, or is there not much of a difference? Because if there's not much of a difference, maybe we should just bias towards reinforcement. And the answer here is it depends. And to explain why it depends, I want to talk about reinforcement baselines and committal behavior. So in the paper, we talk about how for policy grading algorithms, reinforcement is controlled by a term that we call the baseline. When you increase or decrease the baseline, that scales whether you're learning by reinforcement or inhibition. Okay, that doesn't tell us a lot because the baseline is there for variance reduction. And so when we make our baseline too big or too small, we'll end up with higher variance. What does that do to performance? There's this really neat paper by Wesley Chung and Valentin Thomas and their advisors, Beyond Variance Reduction, Understanding the True Impact of Baselines on Policy Optimization, that argues that the role of baselines is bigger than just variance reduction. It scales how committal the agent is. And so what does this mean? What they're saying is something turns out better than expected. We have a positive TD error. The agent can say, I'm all in committing to this action. I'm going to only take this action again. I heard this song. I love it. I'm only listening to that. Or the agent could say, I'm just going to slightly increase the probability of that action. When it goes all in, it's very committal behavior to that action. And it's less committal when it's a small step. Inhibitory or non-committal behavior is when the agent does something and it turns out a little bit better than expected. And it still says, no, I'm going to still do that a little bit less because I don't trust anything. And when something turns out really horrible, it backs way off. So that's committal learning versus non-committal learning. And the paper argues that that has a bigger effect than the variance reduction of baselines. And so reinforcement corresponds to the agent learning or having more committal behavior. So my hypothesis is that reinforcement bias has little impact on performance for non-adversarial environments, but a significant impact for adversarial environments. And by non-adversarial, I mean just a typical grid world where, yes, the agent might initially favor a suboptimal action, but it's not adversarially driven to do so. And an adversarial environment would be something like this chain, where the agent choosing action A2, the blue action, takes it from state 1 to 2 to 3. And when it gets there, it gets a reward of 10, regardless of which action it chose. But choosing action A1 early at any point causes the agent, the episode to end early, and the agent just gets a smaller reward. Why is this a challenging domain? Because the agent's walking along, it's more likely to fail at first and choose action A1 before getting to that state where it gets a big reward. And then it does an update and says, hey, that turned out better than expected. And a committal agent will say, let's take action A1. This is great. Do it a lot more often, which makes it even more likely that you keep falling into that trap over and over. And the agent initially overcommits to the action A1 before it eventually learns that, oh, actually agents. So we'd expect that committal behavior is a big problem here, but less of a problem here. And that's roughly what we saw. That here, the black, these are standard learning curves in RL for this grid world and chain. Black is no bias towards reinforcement. Red is a slight bias, and blue corresponds to only learning, essentially only learning from reinforcement. Almost no inhibitory updates ever. And there's essentially no difference for the grid world, but a massive difference for chain. So the conclusion from this isn't a very strong takeaway, but that reinforcement baselines don't always have a significant impact on performance. We saw that with grid world. And reinforcement baselines can have a big impact on performance, as we saw with the chain. Okay, before I wrap up, I wanted to point out Derek Lacey conducted his honors thesis in fall 2014 that proposes 3 different ways of adding a reinforcement bias to BPO, and then studying the empirical trade-off between performance and reinforcement that each one produces, and they're different is interesting, for Majoku and Atari examples. And we wrote up these at the same time, so some ideas were certainly shared directions, but I encourage you to keep an eye out for his work. And so to conclude, I hope that the takeaways from this talk are Qualia optimization can be formalized. We can write it as a mathematical problem specification. The AEI is natural to include. We want to put something between the agent to transform its experiences and shape the rewards, but that allows for these degenerate solutions, so we probably shouldn't. Many natural quality objective functions are representation exploitable. You might be okay with that, but if you take a computational theory of mind, you might not be okay with that. Examples are the expected sums of reward and the expected sum of TDRs. Reinforcement qualia settings result in naturally representation robust quality objectives, that likelihood ratio, but it's not clear how reinforcement should be defined. There are many directions of future work. I want to talk about just basically the top one. The most interesting question is, can we find some quality objective function Q that's representation robust and that does align with our experiences of what feels good and feels bad? And a starting point could be trying to define reinforcement in a way that fits with this framework. And there's a range of others, but I think I'm over time at this point. Yes, by 2 minutes, my apologies. So I will wrap up there. Thanks.
So, like you take any lower of the Qualia, like what the egg and they topic take million, but
I think, why don't we wait until it clears out a bit, because I'm having trouble here. Let's give it a moment, and then if anyone who wants to stick around, I can. Or perhaps we just take it offline.
Yeah, thank you all. So yeah, if people want to stick around and ask questions, you can do so, but it'll probably be easier. If you need to step out, just please do so quietly. Don't hang around a bit.
Yeah.
I'm gonna have to